Good morning, students. So today's our topic is Kolb's reaction. It is a topic of the organic chemistry in class 12th. Okay, very important from the point of view of ITJ, NEET, and all the various exams. Okay, so let's start with. So this is your Kolb's reaction. Okay, this one. So basically, what is the Kolb's reaction is? It is the formation of salicylic acid. Okay, formation of salicylic acid by the action of pressurized carbon dioxide in alkaline solution on phenol. Okay, so one thing we have to remember that this pressurized CO2, okay, this you have to see pressurized CO2 and alkaline solution, then phenol. So three things are necessary. Okay, so alkaline solution can be made by using a strong base like NaOH, KOH, like that one. And pressurized oxygen is from cylinder. We pressurize into a solution of phenol and NaOH or KOH. Okay. Now the catch is this: when we use NaOH, okay, this one, we use salicylic. We get the salicylic product, the salicylic acid, but the product is ortho. Okay, ortho is the major product. When we are using the KOH here, when we are using the KOH, so the product here we are getting the major product as para product. Both are salicylic acid. Okay, but here it is 2 hydroxy benzoic acid and here it is 4 hydroxy benzoic acid at the para position. Okay, so now let's see this one. Let's go on to mechanism why we are getting ortho and para, and that we will see the detail of this one. Okay, let's see the reaction mechanism. Okay, now we see the reaction mechanism. You can see that first step is the abstraction of proton from the hydroxyl ion. Okay, the OH ion, which is from the base, it abstract this proton. Okay, it abstract this proton here of the phenol, and the sodium ion gets connected to the oxygen negative. Okay, so that is a sort of electrostatic bond, ionic bond, which is created here. Okay, so this is called a sodium phenoxide. Now, the second step, if you see, the sodium phenoxide reacts with the pressurized carbon dioxide. Now, as we can see, carbon dioxide, the carbon oxygen bond is polar and oxygen is getting the negative charge. Carbon is getting the positive charge here. And this negative charge is attracted to the sodium ion because the negative positive attracts each other. And that is a very weak electrostatic attraction, which is formed here. Okay, so that is the second one, and that is important. Okay, I just don't want to miss any detail there. Now the third step is water gives out the proton, and this proton attacks on the negative oxygen. Okay, electron, this is the pi bond, so pi bond electron gets displaced on the oxygen. Okay, and then the carbon is getting the positive charge. So here we have the OH bond. Okay, this one here, you can see that one. So this is the OH bond which is created, and carbon is getting the positive charge. Carbon is getting the positive charge here. You can see that this is the positive charge created by the bond breakage here between carbon and oxygen. Okay, now all this first, second, and third step creates a 6-membered chelated ring. Okay, this one. The 6-membered chelated ring is created here. Now, this 6-membered chelated ring, in this, the carbon positive is attracted towards the pi electron density of the benzene ring. Sodium ion is very, very, good in size. Good inside means it is exactly fitting inside this 6-membered chelated ring. So this 6-membered chelated ring, it is your first carbon, first member, second member, third member, fourth member, fifth member, and sixth member. So it's like this. Okay, so that you can understand here. Okay, this one. So that is your 6-membered chelated ring which is formed, and this chelated ring, in this, carbon positive is about to attack the benzene ring. That is your electrophilic attack. Now let's go on to our next step. That is your fourth step. Fourth step is nothing but it is the electrophilic attack of the carbon positive on the benzene ring. Okay, so carbon positive here where we have seen that this is the carbon positive and it is attacking the benzene ring. It is attacking the benzene ring. So that is the thing. Okay, now next is the electrophilic attack, which is, so this is your electrophilic attack. Now this is very, very easy, the electrophilic attack, which is there. Okay, the electrophilic attack, which is that Now the pi bond, which is present here, you can see this one. The pi bond here, which is present. Okay. Now this pi bond goes to the oxygen and forms the keto, okay, form of this. It is the enol form, and this is the keto form of the benzene. Now in this, benzene has lost its aromatic structure. Now to regain its aromatic structure, the hydrogen from the benzene, okay, this one, you can see hydrogen from the benzene, which is present at the ortho position that you can see here. Okay, it migrates onto the oxygen. So benzene hydrogen migrates onto oxygen, converting it back to enol form. So that is your keto form, and this is your enol form, which is present here. Okay, so that is your ortho product, salicylic acid, and this is the ortho product. Okay, so this is how the reaction goes on. Now coming on to the reaction with KOH. KOH gives the para product. Okay, it also gives the salicylic acid, but it gives the para product. And why it gives the para product? Let's see this one. Now the reaction mechanism, if you see, all the reaction mechanism is same. Okay, but the problem occurs with the large size of potassium ion. This large size of potassium ion doesn't allow, okay, the carbon dioxide molecule, okay, this molecule to attack on ortho position, because the ortho position, okay, is eclipsed by the potassium ion. Okay, this is very, very large, so the carbon which is here, it cannot attack on the ortho position, because the chelation also occurs like that in NaOH. The potassium ion, okay, chelates, or that's a very weak electrostatic attraction. So very weak electrostatic attraction is there, it's present, and due to this electrostatic attraction, carbon, because of the large size of potassium ion, cannot attack on the ortho position. Some students say that it can attack on this side of ortho, but it is also not possible, because the ring attraction, okay, the ring which is formed, and this is the attraction between oxygen negative and potassium positive. So it doesn't, this carbon doesn't come here on this side because of the electrostatic attraction. So this potassium ion doesn't allow the carbon to come here and come here and then attack on this one. So this is not possible for the carbon. So that is the problem with this. So it has to attack on the para position. It has to attack on the para position. There is no other option. That's why we get the para product. Now second thing I want to tell you, that the migration of which hydrogen will migrate to, because it will go to keto form, then again it will go to enol form. Okay, so that is the thing. Now the para hydrogen will migrate to oxygen. If suppose I deteriorate, this ortho hydrogen, and I don't deteriorate the para one, so in the phenol, that is your, sorry, in the hydroxy group, OH group, that will finally form here, you will get a deteriorated, okay, you will get the non-deteriorated. If suppose I deteriorate the ortho, these two ortho are deteriorated, okay, so you will not get the deteriorated hydrogen. You will only get the normal hydrogen, because this para hydrogen is not deteriorated, and with the potassium, attack occurs on the para position. So there is a lot of questions that can be formed here. So you have to understand the exact mechanism. Okay, understand the exact mechanism. So this is the potassium ion problem, because it's of large size. It doesn't allow the carbon to attack on the ortho position. Okay, and this ortho position cannot be attacked because of this bond. Okay, this bond is very strong, not strong, but it doesn't allow carbon to go around and come here, because the oxygen is attracted to potassium. That's why I told you this ring is very important. Even for the potassium, not for even for the potassium and also for the sodium, that the ring is very very important. The sodium size is exactly fitting inside the ring, so there is no problem in attacking on the ortho position. But potassium ion size is very very large compared to the sodium ion, so it doesn't allow the carbon to attack on the ortho position, because the ortho position is somewhat eclipsed. Okay, it is very very crowded, so it cannot, carbon cannot attack on the ortho position. So these are the two three things that you have to keep in mind. Then let's take one question on this. Okay, this one. So there are some MCQs that we can see. So what is the product of the following reaction? So this, we have deteriorated the water, we have deteriorated the KOH, and phenol and carbon dioxide are same. So that is a Kolb's reaction that you know. Now what are the product? What are the possibilities of the product and which is the correct product? Okay. Now oxygen, this phenol, that is hydroxy group. So hydroxy group is deteriorated and carboxylic acid is not deteriorated. So that is first option. Then both hydroxy and carboxylic group are deteriorated. Then hydroxy group is same, means it has normal hydrogen, and carboxylic acid is deteriorated. And D, oxygen and hydrogen, means hydroxy group is same and carboxylic group is also same, means they are not deteriorated. So which one can be the answer? So I want you to pause the video and then analyze, and if you want to see, you can go back to see the reaction mechanism. Okay, so let's see the answer. The answer is C. Okay, hydroxyl group and carboxylic group. So hydroxyl group is same, but the carboxylic group is deteriorated. So why carboxylic group is deteriorated? Because this the H which is coming on the phenol, that's hydroxy group. Okay, it is coming from the ortho position of the benzene. So ortho position of the benzene is not deteriorated. So this hydrogen will be as such. And the carboxylic acid hydrogen is coming from which compound? It is coming from water. So I told you earlier also, so that is your water basically, which is giving out the potassium hydrogen ion. Okay, this one. So this water molecule is giving out the proton. So this green color is coming, green color hydrogen is coming from the water. So water we have deteriorated here. Okay, water we have deteriorated. So after deterioration of the water, there is only one chance, one aspect, that the carboxylic hydrogen will be deteriorated here. Okay. Now, what about the deterioration of KOH? KOH, OH of the KOH doesn't participate. It just take out the proton from the phenol group, means hydroxyl group of the phenol. So that is your OH. So it forms water and that's it. It doesn't go and form the salicylic acid. There is no problem with the KOH. Okay, now let's see this another question. What is the product of the this reaction? Okay, you have to see this one. So there is another question. So sodium carbonate plus carbon dioxide plus water plus phenol. So that is a sort of salicylic acid. Whether it will give what product it will give, whether it will give a product or not, so that you have to see. So one product is your salicylic acid, and that is your ortho product. Another is also salicylic acid, and that is a para product. And then it is your salicylic acid and the carboxylic acid, carboxyl group. The carbon on the carboxylic group is again attacking on another phenol. So that is another product. And option D is your none of the above. So which you will see as the product. Now in this, the answer is, okay, pause the video and just see that one. The answer is D, none of the above. Sodium carbonate here, we took the sodium carbonate as the base. So it is not a very good base. It cannot abstract the proton from the phenol. So if the proton abstraction doesn't happen, because it is a first step, okay, that is the first step. So if proton abstraction doesn't happen, there is no reaction product we will get. So this is all for the Kolb's reaction. I hope you enjoyed the learning, and then we will meet at some other point of time. Okay, bye students.